Be Freeman cute.
I feel so loved right now. Yay. So the solid state, there's a lot of stuff in here that, you know, they don't test anymore. That's on like the Chemistry Olympiad test, for example. And those were the parts of the chapters that we skipped. And so you can go back and look at those, and you should look at them if you're interested in doing well on that. And that'll be something we can do after this god-awful class is over, okay? All right, so liquids, just for background before we start talking about solids, they, the liquid particles, they can move past one another, and that's that translation right there. And how much movement, how viscous something is, how thick something is related to the intermolecular forces that are present. So something like Karo syrup, which is real sugary, high in fructose, you have these big sugar molecules, and it's low in water, and so you have all these London dispersion forces between those big sugar molecules. That's why it's thick and doesn't want to pour out of a bottle. And then if you heat it up, it pours out faster because you're starting to overcome some of those London dispersion forces, just like if you melt candle wax. All right. This unit like changes your worldview, man. In a solid, though, you have to understand with solids, you know, they're not completely stationary. They're in place in a matrix, and they wiggle, but just they don't move position. They don't slide past one another like with liquids. They're held together by intermolecular forces and or chemical bonds. Now, some solids, like molecular solids, are held only by intermolecular forces to make it a solid. And then some solids, like ionic solids or network covalent solids, are held together by intramolecular bonds. Amorphous solids, this would be like wax, rubber, glass. They don't have a crystal structure. The crystal structure is found in crystalline solids, and those are unit cells. All this stuff about the different kind of unit cells, I mean, this is cute. That's great, and these lattice points are the corners, whatever. But you don't need to know these. It's very interesting, but you don't need to know these three different kinds. On the Chemistry Olympiad exam, they'll show you pictures of circles and ask you about like what's touching it. It's pretty complicated, I'm not gonna lie to you, but it is what it is. All right, molecular solids, this is where we kind of picked this up for this class. These are nonmetals, diatomic elements, or compounds composed of two or more nonmetals. As soon as you see a metal in a formula, it's not a molecular solid. These have to be something that is covalently bonded. Okay, so normally they don't conduct electricity because the electrons are in these, they're in covalent bonds. All right, covalently bonded units are held together by intermolecular forces because these things aren't going to have any metals, right? And they're going to be covalently bonded. The strongest intermolecular attraction that you might have would be like a hydrogen bond, right? And so that's when we get ice. Ice is a molecular solid, but still it's pretty easy to melt ice. Soft, low melting points. And so here's two pictures of fats. And so I had talked to y'all about fats and saturated fats. Basically, on every carbon there's a hydrogen. And then you have this little carboxyl group on the end. That's like a trademark of a fat. Anyway, saturated fats have double bonds, and you see when you make that double bond, some of those hydrogens are not going to be able to bond right there. And so that's the difference between a saturated and unsaturated fat. This is going to be a liquid at room temperature because it's going to be less polarizable, right, because there's less hydrogens. Yeah, isn't that fun? That's why, like, olive oil is a liquid, but coconut oil is a solid. Because olive oil has some double bonds in it, and so it has less London dispersion forces, and it's less polarizable. I believe it. But, you know, it's important for you to understand when you hear these things like saturated fat, unsaturated fat, what does that mean? All right. Thank you for picking up my, whatever they happen to be that day I'm talking about. Covalent network solids, these are going to be stuck together by networks of covalent bonds. If you think about it really hard, because everything about this is really hard, right? These are actually really hard. These molecules are, okay. I'm on fire today. Anyway, these contain no intermolecular attractions. They're all one big giant molecule. They're just a bunch of covalent bonds. Yeah, it is super neat, but I don't want to know about it anymore. So when you see something that has carbon or silicon, Si or Si, that's usually a good indication that you're looking at a network covalent. Diamond is one big molecule, which is why it is so hard to cut. Now, if I hit a diamond with a hammer, it will certainly shatter. It is not. It doesn't make it like bulletproof or anything. But I can't cut it because every carbon is connected in a covalent bond to 4 other carbons. There's no weakness in the molecule, and so it's why it's hard to cut. And the hybridization there is sp3 hybridization. Think about it. You have a carbon and 4 carbons around it. How many areas of electron density? 4, sp3. Y'all are so funny. And so, yeah, it's very hard, has a high melting point. And so graphite is actually the same element, and it's a network covalent. It's carbon 2, but look right here, y'all. It has three carbons bonded to it. So its hybridization is sp2. And so sp2 hybridization, when I'm looking at this, like how many electrons is each carbon missing? Yeah, well, there's 2 not accounted for in this shared out kind of situation. So what actually happens with these, pretty interesting, like this is this. It's a plane. It's like that. Okay, and then if I take another flat piece of paper and I lay it like this, these sheets lay like this over and over. Ooh, I can have, thank you, London dispersion forces. Jeez. So they lay like this, and then there are those extra electrons are delocalized and travel through these planes. Graphite will actually conduct electricity. Isn't that interesting? Yeah, and so if I write on my paper, this is what pencil lead's made out of. If I write on my paper, when I glide it over my paper, it sticks to my paper because they delocalize electrons. Yeah. Why does it stick to the paper itself? Well, it comes off in sheets. I mean, it's not stuck to it. That's why you can erase it, right? But what? When you erase something, these are laid down in sheets, and so you're actually, the only thing holding the graphite to the paper would be London dispersion forces, and so when you erase something, you're just breaking up those London dispersion forces. With friction.
When you erase them and you go right again, it's like darker.
Yeah, that's probably just something in the bleaching of the paper. All right, so this gets in sheets. Like I mean, they're showing it here how it's layered, but I mean, it's when we think about pencil lead, we think it this way. So I've showed it sideways. And so here are the delocalized electrons, those pi bonds. And so remember that benzene molecule, that styrofoam ring. Like that's what's happening in graphite. You have that styrofoam, those delocalized electrons between the layers. It does still have a really high melting point because you still have the sp2 hybridization. Can you imagine us having this conversation like 2 months ago? Y'all are like, yeah, that's sp2 hybridization, it's fine. And so, but they are still, these bonds are still very strong inside of the graphite. So, silicon dioxide is glass, it's quartz. Y'all know sand is what you make glass of, right? Mm-hmm. Yes, okay. So sand, the reason sand is at the beach is not because of magic fairies putting it there because they wanted you to go to Florida. It wasn't a scheme by the Florida Tourist Attraction Bureau. But the reason a beach is covered in sand is because silicon dioxide is a covalent network solid. It's very hard, so it's going to be hard to erode, and it is not an ionic bond, so it won't dissolve. So when you get a rock and it's got quartz in it, which is silicon dioxide, after a mountain gets broken down, the only thing left is the silicon dioxide. And so when the river takes crap to the ocean, that's what gets dumped out, and everything else dissolved. And that's why the ocean is salty, because the ions dissolved, but that's why the beach is covered in sand. I feel like the whole world is just a lie. Anyway, this is why glass is really hard. Glass has or quartz has a hardness of 7, and so It is also very hard to scratch. It's the hardest common item. Anyway, so things like rubies and sapphires, that's the mineral corundum, also network covalent bonded. Like any kind of gemstone, network covalent, right? Because you don't want your jewelry to dissolve. All right, now all this mess is really complicated. You don't need to know about this. I'm gonna tell you what you need to know. Okay, so y'all when you did your homework, you saw that silicon is used in semiconductors. Okay, there's N-type and P-type. The N-type is where, all right, silicon has how many valence electrons? 4. Cool. So it's okay. Thank you for trying. Silicon has 4 valence electrons. And so N-type semiconductors dope or substitute, kind of like substitutional alloys. Now this is not an alloy. It's not metal, right? Silicon is not a metal. But N-type conductors, it's substitute an atom that has 1 more electron. If you have 5 valence electrons, wouldn't you be a negative as far as thinking about it with silicon is 4? So anything in group 15, usually it's phosphorus. If you substitute that in, you're going to make a N-type semiconductor. That's all there is to that. So guess what P-type conductors, what group do you think those get pulled from?
13.
That's it. 3A or 13, whatever you like. So anyway, this conduction band and all those pictures and stuff, that's really cute. We don't need to know that. So if silicon is doped, which means some of the silicon atoms are substituted, usually they use like boron, okay? And that's going to make this kind of positive charge build up because they only have 3 valence electrons. So they have 1 less minus sign, right? So anyway, you put the P-type and the N-type together, and there's this potential and charge, and that's how the semiconductors conduct electricity. Yeah, start to build up a charge, and then the flow of electrons is, electricity. And so that's all. I mean, all this stuff is real cute. You don't need, this is physics. I love y'all. I already taught you how the world worked today. I'm out. Peace out. No. Metallic solids. The bonding isn't covalent. It's not ionic either. There's really no feeling about TETs going on. What happens with metals is the electrons are just flowing in the sea. They're just being shared. Like metals are less like free love and electricity for all. Like that's what happens. They just share their electrons. And so the thing about it, you still have your idea about, Coulombic attraction and stuff. The more bonding electrons, like sodium has 1 valence electron, so it will bond with 1 electron. All your other metals, like your D-block metals, like they have basically like a full valence shell. That's why you can have silver at room temperature, no problems. Gold is fine, titanium. Those metals are stable because they are between the d orbitals that they have and their s block. They'll make it so that they have like a stable valence shell. And typically, like you'll have 8 bonded electrons. You don't need to know that, but a group 1 or 2 metal is going to have 1 or 2 bonded electrons. Something in the d block is going to have 8. And so those are going to have higher melting points. That's why we don't build houses and stuff out of calcium, right? But we use things like titanium and iron and nickel and copper. And they're going to have a higher melting point because they have more of these shared electrons holding them together. So let me show you this C. There's the sea of electrons. This is different than the sea where the sand is at, okay? But this would be something, this would be sodium. See how there's one electron for each atom. And so with something like iron, there would be 8 around each, and they're all being shared. So, of course, that would make them also a better conductor of electricity. Are you out? Are you done? This is just too much.
Wait, so if it was a metal, it would have 8 electrons?
Most of, your D block elements, I mean, it varies, but they would have, in this C that's being shared, they're all moving around, just whatever. And so things like copper and zinc and iron are going to have closer to 8. Okay. And so that's going to help hold them together better and make them conduct electricity more and be more stable. Anyway, the reason metals conduct electricity is because of this. They conduct heat because of this. They're malleable and ductile. Malleable means you can hammer it into a flat sheet because the sea of electrons kind of acts like it allows them to act a little more fluid because they're not in a set crystal. And so the sea of electrons is sort of, it's malleable. I mean, that's the word. But ductile means you can draw it into a wire, and there's no direction to these bonds. So it's just like a 3D, just happy sharing festival. Yay, so there is, again, another picture of how these are moving around. No directionality to it. How do you feel? Good. Cool. So let's go ahead and take the answer key 1 through 4. You have to do number 5. And then I want you to work on them, and then the IMF one, and then listen, what you're doing is you're doing the pre-lab questions and also the not page on the lab, not page S5, not that one, not the laboratory questions because you're not done the lab yet. But then the big idea assessments, okay? The more you do on this lab, but to do the lab on Monday, you need to have that done. No bones about it. Pre-lab, and then basically the last sheet. That's your pre-lab, okay? The reason I'm making you do both of those is because we got more stuff to do on Monday. But, you know, I'm about to start talking, and then you're going to have about an hour to work, so that's not bad. All right, anyway, here goes the answer key. Let me pull it up for the people still watching at home. Ha, ha, ha. I feel like this is... Can you kind of see why, so 1 through 4, okay? But listen, I'm talking to you. I'm talking to you about ice and salt. Can you kind of see how the ions interrupt the salt crystal structure? And that's why it's more energy has to be released for it to freeze, and that's why we put ice on roads. All right, here we go. Whee! I will off the video. Are you ready? Hit the lights, Tate. Cool. On your mark, get set, go. Please don't write that much. Thanks. Highest melting point, good times. And then you don't have to do 5. So this is not much. So you need to knock out. I'm making a movie. All right, children at home, here's the lab. You can watch this, and we're basically going to test 12 different solids and test them, you know, melting point. You can test to see if they break easily. You can test to see if they dissolve. You can test to see if they conduct electricity, that kind of stuff. So that's what the background says. Here's the pre-lab questions. So answer them on your own paper. There's 1, 2, and 3, and then, you know, there's really not a flow chart. Like I said, you're going to have 12 solids, and you're going to have to see what kind of solid they are: ionic, covalent, network covalent, I should say, molecular solid, or metal, metallic. I think that's the 4th. Anyway, so if you can test solubility, melting point, so you'll be able to heat it. You're going to be able to crush it. You're going to be able to see if it dissolves. I don't remember if I said conduct electricity, but here's the test that we're going to be able to do. Is it malleable? Does it conduct as a solid? Is it soluble? Does it conduct as a solution? Melting point. And then the goal of the lab is you're going to have a little competition, and you're going to take your 12 things and try to figure out the type of solid that they are. You got 20 minutes, and that's the fun of it, right? Yeah. So here's the lab questions. You don't have to do these yet. You do have to do these. So here's number 1. Let me zoom in a little bit. There's number 1. Okay, A and B and C. And you have to do this before the lab. Number 2 and A and B. Have fun with that.